The next speaker I'd like to introduce is Ciaran Gilligan Lee, Head of Causal Inference Lab and Senior Research Manager at Spotify, who's going to discuss counterfactual reasoning and its applications. And as always, please remember to use Slido for the questions. Cool. Welcome, Ciaran.
Great. Hello, everybody. Can you hear me okay?
Yeah.
Perfect. So my name is Ciaran. I lead the Causal Inference Lab at Spotify. Today I'm going to talk a little bit about the research we've been doing, the problems we've been applying that research to. Before I dive into that, I kind of want to give a quick little motivating example to kind of explain why using causal reasoning is so crucial for decision making so that problems don't arise. So here's a screen grab of a tweet that kind of was put on Twitter around the time of the COVID vaccination strategy during the kind of pandemic in the UK. And this author has found a very strange kind of association that he's reproduced in this tweet. So what he's plotting is on the orange line, we have the death rates of people who have been vaccinated for COVID-19. And on the blue line, we have people who have not received the vaccine. And he's pointing out a very strange thing, which seems to fly in the face of perceived wisdom at the time, which is that there's higher death rates among those vaccinated than among those not vaccinated. So this is data from the ONS, the Office of National Statistics. It was being used by the government as part of the kind of planning for the kind of vaccine rollout and so forth. So this doctor is kind of asking whether it is the right thing to vaccinate all these kind of people and roll out the vaccination kind of policy across the country. So these findings were kind of weird, flying in the face of medical kind of received wisdom. We had randomized control trials that told us that vaccines prevented the spread of COVID, so this seemed very strange. But the findings were irrefutable. The death rates for vaccinated people were far higher than those for unvaccinated people. So it led to the kind of question, do these vaccines work? So a way to try and address what's going on here is to think deeply about the data generation process. So we can draw a nice causal graph here. And when you kind of think about how the vaccines were rolled out in the UK early on in the pandemic, those older and more at risk from the vaccine were given, or more at risk from COVID, were given the vaccine earlier. Those younger, more healthy and so forth, weren't allowed to get the vaccine till later on in the kind of rollout and so forth. So the average unvaccinated person is much younger than the average vaccinated person. So what we have here is that there's a lower mortality rate among those who receive the vaccine, regardless of whether they receive the vaccine or not, just because they're in this older age cohort. So any benefit from the vaccine is being swamped by the increase in mortality with age. So in this context, age is what's known as a confounder. It's influencing both those who received a vaccine and also their mortality rate in the first place. And so what we really should do in this context is figure out what the association or the causal effect is between vaccine and mortality on its own after we've removed the influence of age. In this case, we control for it. And when you do this controlling, if you bucket by age categories, the association I showed in the previous slide flips back. And so those who received the vaccination had lower death rates and so forth. And the ONS quickly removed that previous figure from their website and put in the one bucketed by age so that people wouldn't get the wrong idea like that author of the tweet had done. So what does this tell us? What this shows is that any action or policy change based on those correlations, such as whether to continue the vaccination kind of rollout and so forth, would not have increased patient survival. The take home from this is that relying on correlations extracted from observational data can lead to embarrassing, costly, or in this specific case, dangerous mistakes. And so to overcome this, the reason we're all here today is we need to understand cause and effect. So given that kind of quick motivating example, you might wonder, what's the point of all this for Spotify? So usually when we want to learn cause and effect, we apply randomized control trials or A/B tests to learn about what causes what and so forth. Sometimes you can't do these tests. A lot of examples at Spotify, could be too damaging to the user experience to do such A/B tests. It could be too technically difficult to actually implement. And so luckily we have this causal inference toolkit to try and answer these questions from observational data, as long as we make the right assumptions and don't misinterpret the results in the right thing. So given that we have this kind of framework to answer these causal questions, you might kind of wonder what types of causal questions are available out there for us to answer. So Pearl, it was one of the kind of grandfathers of causal inference in the computer science literature, came up with 3 different layers for types of causal questions that can be answered using this framework. And I'll go through each of these now in turn. So the first one is just standard observation. So this is where kind of traditional machine learning, statistics and so forth lives. On the right, I have a kind of classic DAG here, a directed acyclic graph. That's denoting the classic does smoking cause lung cancer problem. Here there could be an association between smoking and lung cancer. There could also be some genetic factor that's hidden from us, that's latent, that predisposes someone to crave nicotine and also develop health problems as kind of they grow older and so forth. And so any association between smoking and cancer could be biased due to this confounder, as we saw in the example with the vaccine rollout and age and so forth. But at this first layer of the hierarchy, the only question we're going to answer here is, given that somebody smokes, so smoking equals true, what's the probability that they have cancer? So it's a kind of basic kind of observational question. At the next layer, we have intervention. So here, this is what's going to simulate a randomized control trial. So here, in a randomized control trial, we can reach in and kind of force somebody to smoke or not smoke. So any genetic predisposition that might be there, we sever that link because that's no longer what's giving someone a cigarette, it's us forcing them to smoke. And here we can ask the question, given that we've removed that influence from any hidden confounding factors, what is the causal effect of forcing somebody to smoke? So how that's represented is using this subscript here. So the quantity on the lower right-hand side is the probability that someone smokes if we force them, or probably that someone has cancer if we force them to smoke. And the subscript is representing Pearl's do conditional, so reaching in and forcing an intervention in that case. And at the top layer of Pearl's hierarchy are what he calls counterfactual. So these are really the ability to ask what-if questions, imagine alternative scenarios, and so forth. So here we have a slightly confusing mathematical equation, perhaps on the right-hand side. We have the same variable appearing on both sides of the conditioning symbol, which might look strange, but when you say it in words, it kind of makes sense. So the way we would say this equation here is, given the subject is a smoker and they have cancer, what is the chance they wouldn't if they didn't smoke? So the probability on the right-hand side tells us if we observed that cancer equals true and smoking equals true, we now in that context want to ask, what's the probability that cancer wouldn't be there if we had reached in and intervened on that specific individual that has that kind of evidence in the real world? So counterfactuals really are asking questions that are counter to the fact. We've observed some facts that someone smokes and they have cancer, and counter to that fact, had some precondition been different, had we reached in and forced them to not smoke, then we want to see in that context would the outcome have been different and so forth. And so you might wonder, how on earth does one compute those probabilities I showed on the past slide? And Pearl has a nice 3-step procedure for how to estimate these specific counterfactual quantities. So here, if we want to answer that question that we posed at the bottom of the last slide, given someone has cancer and they smoked, would they still have cancer if we had forced them not to smoke? The first step is called abduction. So given the facts we've observed, that they smoke and they have cancer, we now update our knowledge about any latent factors in the model. So it could be that tells us perhaps they do have such a gene, they might belong to that population and so forth. Then in that context, we reach in and do the intervention. So we force smoking to be false. We don't allow that person to smoke. And now in the context where we've updated our knowledge of the latent and we perform this intervention, we now just sample forward in our model and ask what's the probability of having cancer in that context for that individual. So the kind of slightly confusing looking thing on the top can be easily answered by doing these kind of 3 steps here. And to kind of make that slightly more concrete, I have a little example here that kind of illustrates this kind of 3-step procedure. So here I have what's called a disease model. So it's a 3-layer model where on the top I have a risk factor, just being overweight. In the middle I have diseases. And on the bottom I have symptoms. And so in this case, I want to figure out, okay, if I've observed a certain patient has symptoms, I want to figure out, okay, if I turned a certain disease off, if I managed to cure that disease, would those symptoms reduce in that specific patient? So the first thing is I've observed the symptoms in that patient. So that's the first step. I now abduct, I use that observation to update my knowledge of everything else in the model. Now I do the action, so I reach in and I somehow can magically cure this disease if it's present. And then I do prediction, I feed forward, and I figure out, okay, did that reduce the symptoms or not? So that's the kind of 3-step procedure for how to estimate these kind of counterfactual quantities. So Pearl has these 3 levels, these kind of 3 layers, and you might wonder, is just sitting at layer 2, these interventions that just talk about, what a randomized control trial can say and so forth, is that all we need to use in order to make accurate decisions? Or do we need to go to this level to talk about counterfactuals, imagine different scenarios and so forth? So I want to explore this in the context of medical diagnosis. So here again, I have a disease model. We have these 3 layers, risk factors, diseases, symptoms. This was given to us by doctors and epidemiologists who kind of use their domain knowledge to tell us what direction the arrows go, which variables have an arrow between them and so forth. And then from epidemiologists, we get some estimates of what the conditional probabilities are of each of these links. So we assume we have access to one of these big disease models, and we want to use it now to diagnose a patient. So the standard approach to this, and this kind of goes back to the mid-80s, is to use what's called posterior ranking. So just to figure out what disease is most likely given the symptom evidence. And the way I want to now try and do it is by using counterfactual inference. So instead of just saying what disease is most likely, I want to figure out, okay, given that the symptoms are present, I want to now ask, if I had turned off or managed to cure a certain disease, would those symptoms reduce? So given symptoms are present, would they not be, had the disease been cured? So why might the counterfactual approach be slightly better than the posterior inference approach, the correlational approach? So if I go back to this example that I had earlier, if I just look at the standard correlational one, I would have, in this case, output an incorrect disease as the diagnosis. So here, if I've observed someone has shortness of breath, that tells me that perhaps, with some likelihood they belong to a group of the population that's overweight. And again, if they belong to that part of the population, then with some probability, they might have type 2 diabetes. And so now I have an association between shortness of breath and type 2 diabetes. But as you can see from the model, there's no causal arrow from diabetes down to shortness of breath. And so if I had said, diabetes is a good diagnosis for this patient, it would have been incorrect, right? Treating that patient with insulin, for instance, wouldn't have had the outcome that I wanted, reducing the symptoms. But if I look at angina, because there is this causal link, asking this counterfactual question would tell me the right answer. But also it would tell me that diabetes has no connection, because in the prediction step, there's no arrow to link diabetes to shortness of breath. And so here I would have found that actually it's the incorrect diagnosis in this context. And having this counterfactual approach then also lets me distinguish which disease out of the ones that do have these causal links is perhaps the most likely, given that it has these kind of causal connections. Okay, so how do we actually test this hypothesis that counterfactual inference might be better at diagnosing a patient than just standard correlations and kind of posterior inference and so forth? So what we did was we worked with a panel of doctors, and they created 1,700 medical cases that were kind of prepared in a similar way than doctors receive when they're being tested to become general practitioners and so forth. They have to answer certain cases. So here, they're given symptoms and medical history and so forth, and on the back, the panel of doctors has ascertained like one reasonable diagnosis in this situation given all this evidence and so forth. So what we do is we take all these cases and we gave them to our disease model, and now we want to ask that disease model the same question in a different way. So we want to ask it the first time about the correlational approach, the posterior ranking, and the second time we want to ask it the counterfactual approach. So it's the same model, the same parameters, the question we ask it is slightly different. And what we did was we then compared the answers of each kind of approach on those cases to 44 doctors who weren't involved in creating these kind of case studies, and see how these two approaches compared. So the associative approach, this posterior ranking, did pretty good. It placed in the top 45% or 48% of these doctors. But the counterfactual approach placed in the top 25% of doctors, so achieved expert clinical accuracy. What's interesting is the counterfactual approach was actually way better than all the doctors in very rare cases, but not as good as them in very traditional standard cases you might see every day. So that's why the averages were slightly off. But regardless, they're much better than the associative approach. Is interesting, given that the underlying model is the exact same. All we've changed here is we're asking it a different question, one causal, one not. So it's interesting to see this kind of difference here. And what's also interesting, I haven't shown on this slide, is that when you just look at interventions, so not full counterfactuals, but just interventions, the counterfactuals do again better than the interventions, and the interventions do better than the associative approach. So there's this split between the different layers of the hierarchy, which is kind of cool, thus showing why we might need to use counterfactuals to answer the decisions in these given situations. So we published this work in Nature Communications, which was a lot of fun. I was working at a healthcare startup at the time, so it was fun to be able to still publish and so forth. We got a bit of press in New Scientist, which was cool. So here they're kind of pointing out that what we were trying to do was, in some sense, mimic the way a doctor thinks to make better medical diagnoses. And there's lots of evidence out there that humans use counterfactuals to reason about certain situations. So it's cool to see that kind of link there. While I was working on this project, the one thing that really kind of frustrated me was we had this disease model given to us by these expert doctors, and the way in which it was parameterized was we used what's called a noisy OR model. So each node is an OR of its parents plus some noise, and we could fit these kind of the noise parameter to kind of data and have what's going on here. But having a parametric model made it really easy to answer these counterfactual questions. We could just do the 3-step procedure, figure out what the answer was in terms of the model parameters, and then just use that. But if we're just given some raw data in the world and we want to use some counterfactuals, this approach wouldn't be directly applicable because we had this parametric model here. So I've been kind of wondering for a while, how do we do this in a kind of non-parametric way so we could apply it with some assumptions, to raw data that might help us answer decisions in a more kind of wider range of real world settings. So here's my second motivating example, which is going to start this kind of part of the talk. So here we're going to go to the developing world, to Western Kenya, where diarrheal diseases are a leading cause of mortality. And to reduce these, specifically in children in an area of Western Kenya, a local NGO built protective cement structures around the kind of randomly selected group of local wells in order to prevent bacteria from the water getting into the drinking water and then developing these diarrheal diseases. That NGO worked with the Action Poverty Lab, and they found that this spring protection reduces diarrhea in children under the age of 3 by about 25%. So that sounds great, it's fantastic, right? We're having this impact, we're helping these kind of developing nations and so forth. So the question at that point then is, should this intervention be scaled up, right? Should it be rolled out across the developing world where people are drinking from these kind of springs and so forth? In this case, this intervention is expensive, right? To go in, put these cement structures. So we really need to be sure that it will help as expected, perhaps before committing this cost. Maybe there might be an alternative approach that's cheaper, that has the same effect or even a better effect. So really, to answer this question, what we need to do is answer this following counterfactual question. So given a child developed diarrhea after drinking from an unprotected spring, would they still have developed it had they drank from a protected spring? So I can formalize that question in math using the kind of counterfactual notation there. And I now want to answer that kind of counterfactual question. I have the data that the local NGO, the Action Poverty Lab, had. So the question is, how do I do that? How do I answer that question? How do I estimate that quantity? And the way that we approached this was we took a slightly different approach to estimating counterfactual questions. So the first approach has this 3-step action, prediction, abduction, action, prediction approach. But what we're going to do here is talk about a different approach called the twin network approach, which was developed by Pearl and collaborators in the kind of mid-90s. So here, the whole point of counterfactuals is we want to imagine a world that's as similar as our current world is, except for the intervention that we've done. So it's the exact same, except for the slight change counter to the fact in the real world. And we can represent that graphically by just taking our initial model, copying it over, and denoting it as the counterfactual world. And any latents in our initial model are now shared between the factual and the counterfactual world, because latents are outside our model, they're not impacted by interventions, but also we want the two worlds to be as similar as possible, except for an intervention in the counterfactual world. So here, instead of doing this kind of 3-step procedure, all we need to do now to answer counterfactual questions in a twin network is just do standard inference. So we've kind of reduced this 3-step procedure to just doing standard correlational based, statistics, except now it's on this twin network rather than the standard kind of network here. And so this is the kind of power of twin networks, that it reduces things, makes it simpler, but at the expense of having this different graphical representation. What's cool about the twin networks is that the graphical representation of them serves as like a blueprint for a neural network architecture. So we can now try and estimate these quantities by just training a neural network and doing standard ML on it, because we've reduced counterfactual inference to standard inference by going to this twin network picture. So if we construct a neural network whose architecture it matches the twin network, then standard inference on this neural network, when we train it in an appropriate fashion, which I'm skipping over now due to time constraints, we can now answer these counterfactual questions. So to go back to that specific example about the kind of the well in Western Kenya and so forth, when you answer this counterfactual question, what you find is that the probability, this counterfactual probability, is quite small. So it tells us that children would likely have had diarrhea even if the springs had been protected in that situation, which is quite interesting. A similar study reproduced this kind of result in a slightly different way, so it's not like this is a completely incorrect kind of answer here. So it's interesting that asking this slightly more involved question gave us more decision-making power, because it's telling us that actually that intervention perhaps didn't have the effect that was observed. Perhaps that effect was due to when the local NGO came in and put the cement around the wells, the observation that there could be bacteria in the drinking water, the education surrounding that could have had an effect where now it changes habits at home, how the water is drunk and kind of so forth. That could have had nothing to do with the wells. And so further work would be needed in this case before we roll out this big intervention across the kind of the developing world. So this approach to estimating counterfactuals, along with lots of other things, we managed to publish in Nature Machine Intelligence with Athanasios, who was the last speaker before lunch. And we even got a tweet from Pearl, who's the kind of grandfather of causal inference. He kind of points out, and it's a nice way to summarize this result, in that he found it interesting because twin networks, which he introduced, can now be seen as computational instruments that really help us in answering decisions, answering questions that might help us and kind of make more informed and trustworthy decisions and so forth. So again, okay, where does this come into Spotify? How do we use counterfactuals at Spotify to improve decision making, make decisions and so forth? So one we're currently kind of very interested in working on is finding new content for a given user to enjoy. So if a specific user listened to content and enjoyed it, what other content would they have enjoyed? So here we want to condition on, okay, I've seen you listened to this content, you engaged, they're the two facts. I want to now know, had instead I recommended a different piece of content, would you still have engaged? And so estimating this counterfactual quantity can help us understand what piece of content would be good for that user. If we want to figure out, which users need to be shown a promotion, perhaps, or a certain song to engage with that content, or would they find it organically themselves? Here I can ask, I want to find users that if I show them the promotion, they engage, but if I don't show them the promotion, they won't engage. So I want to look at the probability of that joint kind of counterfactual in that case, and understanding those users helps me see who needs to get a promotion in order to engage the content and who might find it organically, and so we don't need to spam them with kind of promotions and so forth. It's because of these connections to finding and recommending songs on Spotify. MIT Tech Review covered our Nature Machine Intelligence paper, which was kind of nice to have counterfactuals in the title somewhere, which is cool. And I was scrolling through Facebook one day and found that Bill Gates had shared the story, which I thought was hilarious. To kind of see that show up on Facebook randomly one day. So that is the kind of end of my talk. Hopefully I've been able to convince you that answering causal questions really helps in making actionable decisions in a trustworthy manner. There's loads of remaining problems to solve. We want to apply these kind of causal inference techniques and tools in the real world to solve real world problems. And there's loads more applications on Spotify, so if you're interested, please let me know. Thanks for your attention.
Thanks, Ciaran. I'll ask the second one first because I think you've almost answered it, but how has counterfactual analysis been used for a Spotify-specific business problem? What was the result? You kind of touched on it in the end.
Yeah. So there's a few ones: promotion, finding a song, helping even artists understand what impact that some of the products that we use to help them gain exposure are having the impact that they wanted to have, and so forth. So there's, almost in every business application that we'd have at Spotify, using causality is super important, like even figuring out, okay, we have podcasts and audiobooks on the platform now, what impact do those have on users? Do they help users retain for longer and so forth? So loads of business problems can be reduced down to causal problems, and I can't speak too much about all of them, but there's quite a lot
Trade
of
secrets.
Yeah, there's a lot of them, and now connecting causality with ML really helps in kind of solving them in a scalable way.
Thank you. This one's going back to the disease model work. What would happen? How would the model work where a patient has multiple diseases? So you talk about people being overweight. That patient could end up with multiple interacting diseases.
Yeah.
How does the model take that into account?
So it starts by looking at diseases individually first, and then grouping 2s and 3s and 4s and so forth, and then figuring out, okay, it could be that a group of 3 diseases, when you turn them all off, that actually had a bigger impact than just turning one off, so that would then jump to the top of the rankings and so forth. But there's various ways we try to speed up that combinatorial explosion that would happen when you grouped all these things together, using the structure of the kind of model and so forth.
How does the counterfactual approach to content recommendation differ from standard recommender systems?
Yeah, I mean it's a great question. So the standard approach, usually, like if you're going to use recommender systems, you might use some sort of collaborative filtering type stuff, where effectively what you're doing is you're finding users that seem similar, they have similar consumption habits and so forth, and you learn about what that user looks like and so forth. But what this is doing is it's just looking at correlations between users, and so that's then liable to kind of make incorrect decisions if you find someone that's similar apart from one thing, and now that one thing is super important for the impacts. We really want to understand, okay, the active intervention of finding, or the active recommendation and finding content for a user is inherently an intervention in your system. It's an action that you're doing to a user. So if you're trying to estimate that from logged data of just correlation, people might be, self-selecting certain content types, and that might then lead to bias in the algorithm and so forth. So if you don't use a causal approach, you can lead to wrong decisions in the same way that the diagnosis algorithm could have made the wrong decision by just looking at correlation rather than causation.
That's brilliant. Who knew when I was running around all that music being chosen for me? But anyway, one last question, keeping an eye on the time. Could you talk about how to get around parametric assumptions in the SCM, e.g. the rank preservation assumption on the noise?
Yeah, so there's loads of these kind of parametric assumptions, which at some level are kind of really important for what's called identifying the causal quantity and so forth, and being sure that you can identify it from certain assumptions. Having parametric assumptions make it much easier to do that. But there are certain non-parametric assumptions you can impose on your model that don't necessarily identify the causal effects. You don't know exactly what it is, but you can partially identify it. You can set bounds on what it is. And so you can say, okay, well, it's definitely non-zero and it's definitely less than this amount. So it exists, but I now haven't had to make parametric assumptions, which could be wrong, to get to that specific answer. And so depending on the situation, you might not believe the model is linear. You might not believe it's even, specifically non-linear in a certain way. And so imposing certain types of weaker assumptions will allow you to put bounds on that kind of causal effect rather than estimate it exactly, and that kind of helps with making the right decisions without committing too much in the first place what your assumptions should be.
Perfect answer. Thank you very much. Thanks, Ciaran.